I'm going to deal with, I'm going to wait for that, the limit as h goes to 0 of the integral from x to x plus h of f of t dt all over h. Let's make sure that, did I do something funky over here? Sometimes I get an autopilot. No, I'm great. I'm golden. All right? And I'm going to show you this graphically. All right. Now, let's go. This is going to, whoa, didn't want to do this. We're going to call this f of t. And I'm going to call this x. Actually, it's more fun. It's more interesting. Excuse me. I got to make a better function, you guys. I'm sorry about that. So I'm going to go from x to x plus h. So let's say that my function does something crazy between x and x plus h. All right? Now, excuse me. I'm going to let's think about this. What could I do that's really clever? Because I'm stuck at this point. All right? I'm going to let u equal the value that corresponds, so this is going to equal to an x value corresponding to the minimum, wow, that's crazy, to the min value of f of t on the closed interval from x to x plus h, right? So it appears in this case that that's going to happen way over here, all right? Maybe I should have had this dip down a little bit lower, but it doesn't really matter, all right? And I'm going to let v equal the x value corresponding to the max value of f of t on closed interval from x to x plus h. So v would be over here. All right, so u is going to be here. It's going to be at this point. So really x in this case is u. However, had this function dipped further down, you know what? Let's just for simplicity and because it's way more fun to prove that way. I'm sorry, I'm being a little selfish here. Let's have this sucker dip down. Let's have it dip way down here. So it's down below. All right, looks like that. So now this is going to be my, let's change the color of these guys. You have to do these kind of one catch as catch can with the cool stuff. So let's make this. This is going to be what I say. U is the min value. So this is going to be u, and this is going to be v. Okay. Now remember one of our properties was, let's write this property down. Remember if we had a max value and a min value, we know that the integral from a to b of f of x dx, this was one of our properties from before, is wedged between the maximum value of the function on the interval from a to b times b minus a, and the minimum value of the function times b minus a. In other words, if you recall, I know that the integral from x to x plus h is going to be wedged between this box and, change my colors, and this box. Oh, sorry you guys. I think I'm getting worse at drawing horizontal lines. And this box, the integral from x to x plus h is wedged between those two boxes. So let's just write that up. I'm not even going to worry about the h yet, right? I think you'll like this. So I've got the integral from x to x plus h of f of t dt is most decidedly wedged between, in this case, what is it? All right, it's going to be f of u times, well, what's this b minus a? Well, it's x plus h minus x. So x plus h minus x is just h, correct? And f of v, because v was my max, right, times h as well, because x plus h minus x. You see how this works, right? All right. Now, I know this kind of seems like an aside. It's like, wait, Ripley, we were worried about this limit. Well, work with me. I'm building a foundation here. What do you notice that both of these sides have? Both have an h. So why can't I divide everything through by h? Let's see what would happen if that happens. If I get that, then doesn't f of u have to be less than or equal to the integral from x to x plus h of f of t dt divided by h, which is going to be less than or equal to f of v. It's got no choice. True? All right, sweet. Now let's look at something. If I take the limit as h goes to 0, well, let's go back to this guy right here. If I take the limit as h goes to 0, what happens? Well, this guy is going to head back. If h goes to 0, then x plus h heads back to x, doesn't it? Which means that these maxes and mins are going to float along this function like a bead on a wire. And what's eventually going to happen? Well, they're always wedged between x and x plus h, right? So if I take the limit as h goes to 0 of f of u and take the limit as h goes to 0 of f of v, well, remember, as x plus h slides back, because u and v are always wedged between, they're going to slide back as well. Aren't they both going to be equal to f of x? They have no choice. Again, they're always wedged between x and x plus h heads back to x as h goes to 0. Which implies, if I take the limit of this whole thing, h goes to 0 of f of u, right, which is less than or equal to the limit, or excuse me, an integral from x to x plus h of f of t, the limit as h goes to 0 of this guy, which is less than or equal to the limit as h goes to 0 of f of v. Well, we know from this little observation right here, we know that this guy goes to f of x. We know that this guy goes to f of x. Well, remember the squeeze theorem or the sandwich theorem? If both of these guys go to f of x, what must this guy go to? You guessed it, f of x. Guess what? If the limit as h goes to 0 of the integral from x to x plus h of f of t dt over h equals f of x, well, don't we know that this is equal to g prime of x? That's how we defined it right there. This was g prime of x, and we did it. We proved it. That is the proof of the fundamental theorem of calculus in a nutshell. We proved that the derivative of an integral is the integrand, as long as that integral is not definite. Remember this, the thing that's really important, and I always have students just get crazy with this. Remember this, if I take the derivative of the integral from 1 to 5, or now let's be a little more general there. If I take the derivative of the integral from a to b of f of x dx, well, what is this thing? It's a constant. It's a number. So the derivative of a constant is always 0. However, if I take the derivative of the integral from a to x of f of t dt, and this is always going to be, g, slow down there, little cowboy, this is always going to be f of x. And that's what the fundamental theorem of calculus guarantees us. Now, the fundamental theorem of calculus part 2, once you have the fundamental theorem of calculus part 1, it's really easy. But we've already used this guy. I know the integral from a to b of f of x dx is equal to capital F of a minus capital F of b. This is just an extension of the fundamental theorem of calculus, which can be proven relatively easy. Okay, now, that's it. That's all I'm going to do with you guys for today. I just wanted to show you that. It's really cool. In class tomorrow, we're just going to do a bunch of these. All right? We're going to do problems over and over and over again that deal with the fundamental theorem of calculus. Okay? So we'll have a little fun with that. Hope you enjoyed. Have a great day.